Welcome to solverfy.
Okay, so for problem number 58, we're asked to calculate the Q value of the reaction when a negative pion collides with a proton to form a neutral lambda plus a neutral pion. Now, we're given the fact that the proton is stationary, and it wants us to estimate the minimum pion kinetic energy in order to form this reaction. So first, to calculate the Q value, so Q is just equal to the sum of the difference of the reactants and the products mass energy. So that's just m mass of the pion c squared plus the mass energy of the proton c squared minus the mass of the lambda c squared plus the mass of the pion. So we can now plug this in. We know all these numbers from the table, from table 2. So we have 139.6 MeV plus 938.3 MeV minus 1115.7 MeV plus 497.7 MeV. So this equals minus 535.5 MeV. So that's the total energy that we need to add to the system in order to allow this make this reaction possible. So now, to figure out what the kinetic energy, the minimum kinetic energy required for this to happen, we need to kind of just think about what we know about the problem here. So we're given the simplification that when the reaction occurs, the lambda and the pion move off with the same velocity. So since they're moving with the same velocity, we can treat them as a combined mass moving together. So where we'll call it big M is equal to the mass of the neutral lambda plus the mass of the neutral pion, which is equal to 1613.4 MeV per c squared. So that's the mass, not the mass energy. So now, using conservation of energy, we can make the statement that the total energy of the big mass here is going to be, or on this side, is going to be equal to the total energy of the pion plus the rest mass energy of the neutron, since the pion is carrying some kinetic energy and the proton is at rest. Now, also, momentum has to be conserved across this, and so the momentum on this side has to equal the momentum on this side. Now, the only thing that carries any momentum on this side is going to be the negative pion, because it's the one in motion. So we can state that the momentum of the negative pion is equal to the momentum of the large mass on the other side. So we also, looking at the relativistic energy term, is equal to Pc squared plus m0 c squared, fourth, I should say. And then we can rearrange this to state that Pc squared is equal to the total energy squared minus the rest mass energy squared to c to the fourth. And now from that we can put this in the form minus c squared is equal to momentum times speed of light squared of both. So now that that's in this form, we can now plug in some of the things that we know. All right, so let's go ahead and plug in what we know. So we'll plug in the total energy, so the kinetic energy of the pion is equal to the total energy of the pion squared minus its rest mass squared, which is equal to the total energy of the big mass squared minus its mass squared times c to the fourth. And then we have this relationship that we've already set from conservation of energy. We can plug that in to this guy. And so now we can rewrite this and say e pi minus squared minus mass energy of pi, c squared squared, so actually squared c to the fourth, keep doing that, c to the fourth is equal to e to the pi minus plus the rest mass of the proton squared minus the total mass squared c to the fourth. And then we can expand this, and we can state e to the pi minus squared minus its rest mass squared c to the fourth is equal to e pi minus squared plus 2e pi minus m mass of the proton c squared plus m squared c to the fourth minus big M squared c to the fourth. All right, so right away we can see that these cancel. And now we can rearrange it because we want to solve for this term. So we can rearrange this now, and we can put 2 pi minus 2e pi minus mpc squared is equal to, so that's, then we bring over that. So and we add that, so we have m squared c to the fourth minus m pi minus, don't confuse that to minus 2, so put that down a little lower, squared c to the fourth minus mp squared c to the fourth. Now we solve for the total energy of the pion. We're given e pi minus is equal to mass squared c to the fourth minus m pi minus squared c to the fourth minus mp squared c to the fourth divided by 2 mpc squared. All right, so now this is equal to, so this is the total energy of the pion, so that's going to be its kinetic energy plus its rest mass energy. I'm going to now create a new page here. I'm going to rewrite that equation from the last page just so it's here. So kinetic energy of the pion plus m pi minus c squared is equal to big M squared c to the fourth minus the mass of the pion squared minus mass squared of, I keep doing that, sorry, please bear with my little mistakes as I go through this. That's to the fourth, that's squared, so it should be mass of the proton, so mass of the proton squared c to the fourth over 2 times the mass of the proton c squared. Okay, now we want to solve for the kinetic energy of the pion, so we can just move this guy over. Kinetic energy of the pion is going to be equal to m squared c to the fourth minus m pi, the negative pions, squared c to the fourth minus the mass of the proton squared c to the fourth divided by 2m mass of the proton c squared minus mass of the pion c squared. So now we can plug in all the numbers that we have because we've solved for, we know this term, we know all the rest of these terms. So we can say the kinetic energy minimum kinetic energy of the pion is going to be equal to 1613.4 MeV squared minus 139.6 MeV squared minus 938.3 MeV squared divided by 2 times 938.3 MeV minus 139.6 MeV. And working out all those numbers, we get the minimum kinetic energy of the pion must be 768.0 MeV. And there we go.